Hello everyone, today I have a really fun problem for you and we're going to be learning about lattice polygons and Pick's theorem. This is an AMC problem and we're going to see how we can use Pick's theorem to very easily solve this, and we're also going to see what if you don't know Pick's theorem, what do you do in that case, right? So let's get started. This is problem number 4 from the AMC 2018 and in this video we're going to be learning Pick's theorem and lattice polygons. So the problem itself is relatively quite simple, but the main takeaways are going to be the concepts of lattice polygons and Pick's theorem, right? Introduction to that. And then we're going to see how to solve the problem without the knowledge of Pick's theorem. Then we have certain book suggestions for the AMC, and at the end we have a symbol.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
So it's given to us that a 12-sided figure is shown, and it has been drawn on a 1 centimeter by 1 centimeter graph. So this is basically a coordinate graph or a lattice graph, whatever you call it. And what's the area of the figure in centimeters square? So we're going to first see the method of Pick's theorem, but before we get into Pick's theorem, I want to get clear with certain definitions, right? So what are lattice points? So lattice point is a point in which points for which both coordinates are integers, right? So what that means is if we have a point m comma n is a lattice point if and only if m comma n belong to integers. So both of them are integral, right? So m comma n is a lattice point if and only both m and n are integers, right? So for example, 3 comma minus 2 is a lattice point, right? And then what is a lattice polygon? And after this we have lattice polygon. So as the name suggests, lattice polygon is nothing but a polygon that has all its vertices as lattice points. Okay, so all its vertices are going to be lattice points, right? So for any vertex or all vertices are going to be m comma n, such that both of them are integers, right? So that's what a lattice polygon is. And what is a Pick's theorem? So Pick's theorem is basically a formula given for the area of a lattice polygon, right? And this formula basically states that the area of a lattice polygon A is I plus B by 2 minus 1. Now, this formula is actually valid considering that there are no holes in the figure, right? So, for example, we have a lattice polygon. For example, we have this lattice polygon. So assuming that all of the vertices over here are lattice points, and this figure is obviously does not have any hole in it, right? So if you have a hole in it, we kind of need to subtract the area of that hole, right? But the Pick's theorem basically says that a plus b by 2 minus 1. Considering that there are no holes in it, we have a generalization as well. If there are holes in it, but in most cases we need some other information as well. But for this question, as given the figure there were no holes, we can really use the Pick's theorem, which is a is equal to I plus b by 2 minus 1, where a is the area of the lattice polygon. I is basically number of lattice points in the interior. Okay, lattice points in the interior of the polygon, right? And what is b? B is the number of lattice points on the boundary. So I for interior, b for boundary. It's kind of a way to remember that, right? B is the number of lattice points on the boundary of the given lattice polygon. Okay, perfect. So now let's move on to the problem, and let's actually see what was given to us over here. So if I just try to use a is equal to I plus b by 2 minus 1 over here, and let me just try and calculate the value of I. What is I? Is the number of lattice points in the interior of the polygon. So we have number 1 over here, we have number 2 over here, 3, 4, 5, 6, 7, and 8. So I would be 8. Let me try and find out the value of b. B, what is b? Number of lattice points in the boundary, right? This is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8, this is 9, this is 10, this is 11, and this is 12. So your b is 12. And now if you just compute this, that would be 8 plus 12 divided by 6 minus 1, that is nothing but 13. So 13 is the correct answer, and that can be easily figured out using this concept of Pick's theorem. Now, what if you don't know Pick's theorem, right? Let's say you did not know this. Let's say you had no idea what this Pick's theorem is, right? It's an AMC 8 problem. So, as an 8th grader, I can understand if you do not know what Pick's theorem is. You might have not even heard of that term before, right? But this problem is actually pretty simple, and it can be solved without Pick's theorem. And all of these are 1 centimeter square. So, the area of this one square, if I just shade this, area of this entire square is going to be one centimeter square. And the area of this triangle is going to be half, right? As the area of the triangle is half of the area of the square. Pretty simple, right? We just need to find out the so what about the area of this? Area of this would be x plus y by 2, where x is the number of squares and y is the number of triangles. Why? Because the area of one square is going to be 1, and the area of one triangle is going to be 1/2, right? So the total area would be x plus y by 2, where x is the number of squares and y is the number of triangles. So if I try and find out x, what would be x? X is 1, 2, 3, 4, 5, 6, 7, 8, 9. And what is y? Y is 1, 2, 3, 4, 5, 6, 7, 8. And if I just substitute this and compute this, I'll get a is equal 9 plus 8 by 2 is 4, so a is equal to 13. So with both methods, we can really see that the answer is 13. So yeah, that was a pretty cool application of Pick's theorem. Now I know that although you do not need to use Pick's theorem, and most likely you will not use Pick's theorem for this question, but definitely certain questions can be formed in which you will for sure have to use Pick's theorem. So for example, if there was a hole in this figure, right? There is no hole, but assuming there was a hole in one, you would have to use the generalization of Pick's theorem. Okay, so I hope you enjoyed that, and it was a really cool problem. And we have certain book suggestions for the AMC. Mathematics Can Be Fun by Yakov Perelman. We have Mathematical Circles, the Russian Experience. We have Algebra Can Be Fun by Yakov Perelman. We have An Excursion in Mathematics and Challenges in Physics of Pre-College Mathematics. Okay, perfect. So now we have a similar but challenging problem, and this is kind of like a more rigid problem in which you would have to use Pick's theorem. And there are a couple of ways to solve this. So one of them is using Pick's theorem, which is probably the easier method. I would recommend you to use that to kind of get a hang of the Pick's theorem. And the other way is to use the shoelace formula. What is the shoelace formula? It's nothing but the area of a polygon using coordinate geometry. You might have seen that in elementary coordinate geometry as well. We find out the area of the triangle using that similar idea. Right, so you can either use the shoelace formula, or what I would recommend is use the Pick's theorem, because the question is potentially a little bit easier that way. At least I found it to be. Right, so as usual, if you make any progress on this or if you're able to solve this, let me know in the comment section below, and I'll be sure to respond. Until then, this is it from me, and I'll see you in the next video. Bye bye.
Cheenta programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.